Yes, I'm going to speak about this moment problems in robust. Well, I already said this, and I would like to give first some recognition to two people here, and a number of others that are added there also. But you know, there is Chris Burns, as you all know, and who actually went away. Actually passed away a couple of years ago in Stockholm. When I invited him there, so. And then Tryphon, still alive and well, and of course we've been working quite a bit together on many things. And then you have a lot of other people there, including several students and etc. Now, what is this talk about? Well, really I'm going to talk about the very classical problem, the moment problem. But it has a decidedly non-classical twist to it, which is really motivated by applications to engineering and control. And what is new here are certain rationality constraints imposed by applications that alter the mathematical problem and makes it nonlinear. That may seem like a bad idea to make a linear problem nonlinear, but actually that turns out to be quite fine, you know, as we shall see. And then we're doing a global analysis approach that studies not just a solution, but a whole class of solutions, so that you can use this class of solutions and tune it to the other specifications. And in this case, we get a sort of powerful paradigm for smoothly parameterizing, comparing, and shaping solutions to specifications. So this is sort of the engineering twist to this mathematical problem. So let's look at the moment problem. Well, given a number of numbers here, C0, C1 up to Cn, you want to find a positive measure, so that if you integrate it against certain linearly independent basis functions, the alphas here, alpha k's, then you will actually get these numbers. So that's the moment problem. And you can already see here that the moment problem, if there is a solution, it will in general have infinitely many solutions, right? So therefore, we have a leeway of creating solutions that are good for specifications, right? And here are some possible basis functions. For the power moment problems, there are the monomials. For trigonometric moment problems, there are the trigonometric monomials, and for Nevanlinna-Pick interpolation, you have these Herglotz kernels. And I mean, this is an old problem. Here are some of the guys that worked on parts of this, at least the power moment problem. Chebyshev and his two students from St. Petersburg. You know, you can see the difference between the advisor and the two students. They all have beards, of course, but you have to have beard to work in the moment problem. But you know, you see the young guys there; they have black beards. You know? Okay, so this is it, and here we have the moment problem. Here's an example to show that they're really intermediate solutions. Let's assume that we use a step function, you know, for mu. Then clearly what you get is just a bunch of linear equations, right? You have a system of linear equations like this, where you want to find the steps here, the x's, given the c's, and since capital N here is much larger than n, and these are linearly independent, these functions, you have actually infinitely many solutions, right? So you can even see it for such a solution. Now what we want to do here is looking at the absolutely continuous solutions like this, where this phi is a spectral density, because then you can see that these are just the moments are just in this case this is one case. This is another example where the moments are just the Fourier coefficients of the spectral density, right? So, where do you find moment problems like this? Well, you find it almost everywhere, although it's usually not, many people don't recognize them as being moment problems. We get them in spectral estimation, speech synthesis, system modification, image processing, optimal control, robust control, model reduction, model matching, etc., etc., etc. You know, so they occur of various types, and of course, then may not be treated in this way because in general. But I mean, I just want to see that here is a whole. You can make moment problems in many applications in these areas. And why do these problems require a non-classical approach? Well, solutions must be of bounded complexity, such as rational or bounded degree, so that one can realize it by a finite dimensional device. You don't want to go down to Radio Shack and say, give me infinitely many of these components, right? You want to have a finite number, okay? So you want to build something. And of course, if you look at the transfer function here, we know from from Kroneker's theorem that the system is finite dimensional if and only if the transfer function is rational, right? This is old engineering knowledge, right? And classical theory does not provide a natural parameterization of rational solutions of bounded degree, so we need to do something different, right? Now, let's do a prototype problem, and this is a covariance extension problem. This is, so let's say that we are given a number, there's actually an underlying stationary process here, and we have these covariance lags, which are, of course, depending on, not on t, just on k. And we're given now a finite number of these, c1 up to cn. Find an infinite extension of that, so that if you form this function here, it's a so-called Kara-Theodori function. So it's analytic here in the disk, and it maps to the half-plane. If you have it outside of the disk, you call it positive real, right? But of course, this is the same. You can do either. And this is the Kara-Theodori extension problem. Actually, this was completely parameterized. The solutions of this were completely parameterized by Schur in a famous paper from 1919, I think, where he actually parameterized the solutions in terms of reflection coefficients. We now call them Schur parameters today. This is so this was a complete parameterization of all the meromorphic solutions. Now, meromorphic solutions, they're like rational, but they are infinite dimensional, right? Systems that would be. So you know, they're not quite rational functions. So this was all of these functions. But what if we say that it had to be rational degree at most n? This is actually a problem that was posed by Kalman, and actually he was a little bit obsessed by this problem for a long time. This was during his algebra time. Remember his algebra time, when everything should be algebra. And so he said, no, what you should do is to take the Schur parameters from this 1919 paper, and you do algebra on the Schur parameters and see what are the conditions that are needed to make it rational. Now this is not, now today we understand that's not a good idea at all. But this is what he gave to Trifon as a problem to do, among other things. And Trifon didn't obey him. He didn't use algebra, he used topology and analysis instead. You know, so this is actually the thing. And so now let's look at this. This is also a trigonometric moment problem, because look at this. Here we have this. Now let's take the spectral density, which take 2 times the real part of f of z, evaluated on the unit circle, right? And you see that you get the 2 tails here, so you actually get precisely this thing here. So the 2 tails have to share the constant term. And that, of course, to be a spectral density, has to be non-negative, right? So this means that, first of all, you will have this to be analytic here, because you know it's around 0 here. So we have the analytic and in here the disk. And then it maps into the half plane because you have to have this condition, right? The real part has to be positive, not negative, right? So this is the Carré-Theory function. And this can be written as a moment problem here. Find a phi of degree at most 2n, such that this moment condition, the geometric moment condition is fulfilled. And also phi is going to be a ratio between two trigonometric polynomials, right? So this is the thing. This is what we wanted to have in a covariance extension problem, right? So here is a little slide. Let's assume we have one of those systems, and we just feed it from long time with white noise. And we think that it's stable. And then after a while it's going to become a stationary process, right? Coming out here. And this stationary process is going to have this spectral density. The W evaluated unit circle absolute square, right? Now, that is of course the Fourier coefficients of that are precisely the C's. And the C's are those are the covariance lags. Now what we're doing is really observing here. We're observing theta, right? So if we had time to do infinitely long observations, which of course we don't, then we could form this thing. And this limit, this is an ergodic limit that under conditions here will converge, and that we can write it like this. But you know, we don't have infinite number of data. We have finite number of data, capital N. So we have to use some kind of estimate. We use this ergodic estimate, and we cut it off after capital N, right? And then of course, then actually we can only estimate C0 up to C little n, where little n has to be much smaller than capital N, because otherwise this estimate becomes very bad, as you can see. If we have it close to capital N, I mean there are no terms in it, you know. So we have to have it like this. So that remains to determine the rest of these guys. Now you could pretend that this is just the ordinary cases, like we do the Hankel thing, you know, as we use, etc. That's what people do in subspace identification. And for years, I used to, and European and we used to go into the meeting and I said, look, that's not, they say, oh, sometimes it doesn't work. This is numerical problems. No, it's not numerical problems, it's theoretical problems. Because what you get is not a Carré-Theory function, possibly real function, in some of the cases. You know, so actually, because there is something like this, if you have you partial realization, and you have a sequence of numbers, and the Hankel matrix rank is going to be sort of algebraic degree of this thing. But the positive degree, the smallest degree, so it's also positive real, it could be higher, could be twice of that, and I mean generically. And there is no generic degree, positive degree. So this is one of the things why they had a much of fixtures in subspace identification, you know. So with two students, I really even had to make a counterexample. We made a counterexample, simple, a very devious one. So with one-dimensional one system where they could take any white noise through it and get data. And all of these subspace identification would fail with 80% chance at least, right? You know? So this is when they started listening to this. So this is a lot of fixes came in at that time. Now this was a parenthesis because this is not part of this. Well, it's sort of part because I said identification too, right? Now, so let's take the modeling of speech. Take this as an example. Well, in modeling speech example, you have a system like this. You have an excitation signal goes in, and speech comes out. And of course, this would be very boring speech if this didn't vary with time, right? Okay. So what you do is that you have the speech signal here and you divide it into short intervals. And I don't know whether it's 30 milliseconds now. You will know this better, but I think it is. And the mobile telephone. And then it cuts it out like this. And then you take on each of these. Just think of the process being. This is like 1/5 of a phoneme. And you think of it as a stationary process. And it can be modeled precisely like a constant W like this. And here's a 30-minute frame of speech from the voiced nasal phoneme. Okay? This is a difficult one. And here is the parallelogram, the fast Fourier transform, right? Now, if you're talking with your wife on the telephone here, this is too much information to send because it has too much thing like this. You don't want to have this. You want to have, what you want to do is to construct a rational filter with a rational W, the transfer function, of low degree modeling the window of speech. So that you have a filter determined by a few parameters. And then you may get an envelope like this. And that's the one you would use, right? Okay. Now, how are you doing this in the telephone? Well, you do linear predictive filtering. This is the easiest solution to the model problem, right? This is the simplest one. Actually, it's always linear. Actually, essentially you solve normal equations like this, which you can do by using, this is the tuple structures, you can use Levinson algorithm, right? And if you take these things here, and you take them as coefficients in a polynomial here, this is the Sago polynomial. These are the polynomials orthogonal on the unit circle, right? And then the transfer function here is really this one. It has all its zeros at the origin, and this is here down. It has this polynomial, Sago polynomial. Like this. So this is how you construct it. So here it is. Okay. And in the telephone, you take n equal to 10, right? So here's what you do. You choose an excitation signal from a code book with 2 to the 10 entries, 10 bits, right? And you check which one is best, and then you. As this is a very simplistic way of saying this, but this is what I see it. And then you send it together with the coefficients of the Sago polynomial, 10 squared, and to this thing. And there you build a filter. Okay, take the signal out of the code book, get it through there, and you talk to the person, right? Okay? Now, but couldn't we do something better by choosing this numerator here not to have all its zeros at the origin, right? Let's look at that. Here, let's look at this thing. Now in the cellular telephone, you have this transfer function, right? Here is what it is. What can you see? This is a bit flat. And why is it flat? Well, if you think about it, the spectral zeros are all here. And the action is out here on the circle, right? That's where you integrate. So the zeros are actually as far away from the action as possible, right? So this means, think about analytic function. What I learned about analytic functions was that this was like a rubber sheet of the complex plane, and you pull it down somewhere, it follows down, right? And of course, if you have a zero closer to the unit circle, it will pull down on the unit circle too, right? And if it's far away, it won't pull down so much, right? Okay? So this is like an analytic function. So, can you do this? This is actually what Trifon asked himself in his thesis. Is there a solution for each choice of spectral zeros? Like this. And yes, there is. And he also conjectured that it's unique, which are also well posed. So this is what we did with the relation there, right? Now, so here it is, the solution of the rational covariance extension problem are completely parameterized by the zeros of the corresponding shaping filter. I give an arbitrary monic stable polynomial. There's one and only one stable polynomial such that this is a shaping filter for this. And the correspondence is a diffeomorphism. Now, why is it good with smoothness condition? Well, if you're sitting there and you want to tune it, tune the parameters then you don't want it to go like this, right? You want it really to go smoothly with your tuning, right? So therefore the diffeomorphism, of course, will tell you this, between the spaces here that I didn't define, but you get ideas, a smooth map. And this is really what was done here. Yeah. Right. This was non-constructive in the beginning, but now we have a constructive proof based on optimization. Well, now this has been around for a while now. Here's an example. Here we have this thing that I showed you. All the zeros in here, and the poles are the red ones out here, right? And this is that one. Now, let's say that we move the spectral zeros. You see, we might want to move one of the spectral zeros at this frequency to pull down closer to that frequency at the unit circle, right? And we're pulling it down, right? The rubber sheet. Okay? So this is what you can do here. You have the frequency here is probably this zero here is going to have very close. It looks like it looks on there, but it's close to the unit circle. And then, of course, you also move the poles accordingly, right? So you actually, this is a way, it has an idea for tuning, right? And here you have a 10th degree. Here you have a 20th degree. Still doesn't do the work, if it's have to see. This for 6th degree, and now it pulls down, there. So this is the idea of tuning. So what we have here, okay, we have an optimization approach. So given sigma, the numerators, spectral zeros, and C, we have a function with a linear part, a variable q, q0, q1 to qn. So we have a linear part, and then we have this logarithmic integral, where capital Q is the trigonometric polynomial with those parameters, right? Those kind of variables. And that has to be greater than 0. You want it to be, so, okay? And you see then what is the boundary here is, of course, when this has a 0. When this has a 0, this log goes to minus infinity. There will be plus infinity with a minus sign here. Of course, that doesn't mean that the integral goes. The integral is still finite, but of course it does make the integral bigger, right? That's the intuition, right? So it kicks the solution into the interior, right? Now, if you look at this a little bit more that we've done later, you see that there are a lot of situations where you have to be careful with this, because if you get the spectral zeros on the boundary, or is it more dimensions than, the dimension I mean the number of variables, right? Like you do moment problems for imaging, for example. It could be 2 and 3 is the usual. Then it could be that there's a lot of things that can happen, but you have the same paradigm, the same entire paradigm. And the theorem is that there is a unique minimum. Of course, this is strictly convex. So if there is a solution, it's unique. But you have to prove there is a solution, right? And then you solve it, you get your Q, you do spectral factorization like this and get an A, put the A in here and solve this linear system, and now you have F is B over A and W is sigma over A, right? So this is how you would solve this. Here is actually something that I thought is sort of cute, that I did. Let's normalize the coordinates, so that's C0 equal to 1. We divide by C0. Then the space all rational Carathéodory functions f of degree at most n is a 2n dimensional manifold. Now, I can't draw a manifold with high dimension here, so I'm going to draw one with n equal to 1, okay? But what I'm saying is true. So the picture illustrates what is true. So if we do this in certain coordinates here, which happens to be a true parameter there, and this is then this thing here, interior of that, open interior, is the manifold, of course, two-dimensional manifold, right? Now, there is a foliation with one leaf for each choice of sigma. This actually comes from the fast Kalman filtering a long time ago. What is a foliation? A foliation is really like this. Those of you that didn't do the differential geometry, foliation is this: you have a manifold, and you can divide this manifold into submanifolds called leaves. That's why they're green, right? These are leaves. And so that each point in the big manifold lies on exactly one leaf. And these leaves don't intersect, and they are smooth. Okay? So this is basically what a foliation is, right? So there is one leaf for each choice of this. Now there's another foliation with one leaf for each choice of covariance sequence. Okay? And these two intersect transversely so that each leaf in one meets each leaf in the other in exactly one point. Okay? So this is unusual, in many applications that you get intersecting foliations like this. So this is a very lucky coincidence with this particular problem. Right? So this means that you come to me, you have a covariance sequence. There's this covariance sequence here. And I says, but I don't like this maximum entropy one, LPC. So I asked, what kind of spectral zeros do you want? Well, I like these spectral zeros here. Well, then you're on this foliation, and you're on this foliation. This is your solution, right? Okay? Now, how do you compute it? Well, you can compute it by convex optimization, right? Okay? Actually, we had this result before we had this result, so. So that's what this is basically the paradigm that we're going to work in now, So you can say here's the global analysis approach. Find complete parameterization. You have a complete class of solutions satisfying complexity constraints. Find a set of tuning parameters, have a smooth bijection between them, right? So you move the parameters here, you move a little bit here, right? And for any choice of tuning parameter, determine the corresponding solution by convex optimization. Choose a solution that best satisfies the additional design specification without increasing the complexity. You see, you are in the same complexity class. You don't change the complexity. Okay? Same complexity as the maximum entropy solution. Now, what other applications leading to moment problems? Well, here is an example, Nevanlinna-Pick interpolation. Now the basis functions are these Herlot's kernels. And the Nevanlinna-Pick interpolation thing is this, that if given a number of points in the disk, we take them distinct now. We don't have to take them distinct, but for this talk they are distinct. And then we have a number of values here over and here. Those are the C's. And we want this function to interpolate these to the corresponding C values, right? Okay. Now what makes this not Lagrange interpolation is that you have to have functions of this type, Caradori functions, right? That's the difference. And it turns out that this problem is the same as this problem. You can rewrite this like this. And here you have like the spectral density again, right? Okay. So that's a problem that looks like what we had before. Only thing is we changed the the trigonometric monomials by this Hertz's curve. That's the only thing we've done, right? Here's an example. Well, actually what we did before, we can think of the covariance extension problem, the one I started with, the Kalman, the one the Kalman liked. That could be thought of as a Nevanlinna-Pick interpolation, not with this thing, but all the integration, all the points, all the interpolation points at 0. Because you have evaluate 0, you have the derivative evaluate, the second derivative evaluate 0. That's also Nevanlinna-Pick. So you have all your interpolation points there. What we did then, we moved the spectral zeros from the origin closer to the unit circle, so we can tune it from maximum entropy to something else, right? Now why don't we do the same thing with the interpolation points? Okay? Why would that be good? Think about this. You are a cop, and he's speeding in his car, right? And you have your Doppler meter there, right? And you want to see that you are going to measure between, what did you do? Between two lines, okay? Spectral lines there in the spectrum, to see how far they're away, so he's speeding, which of course he is. Because he's a French, you know.
Actually, Belgian.
Oh, I'm sorry, yes. Yeah. But you speak French.
We're talking in metaphors.
Yeah. I know, but it's not word, but you speak French. Yeah. So anyway, what happened here is that you don't care about the whole spectrum. You don't care what's happening over this part of the spectrum this way. You want to just have a small, narrow piece of the spectrum. So why not use all your efforts to go into this thing? That means moving all the interpolation points close to this part of the spectrum. Because then you zoom in, right? Okay? So the idea is that to do this here now. Let's see. Here's an example. Tunable high resolution spectral estimator. Zoom into a selected band by moving interpolation from the origin close to the unit circle. So, and then what you do is this. Here is it. You have an observed process. This is one way of doing it. This is much more. I can make this much more complicated, but I won't do that. And then you have these things here, and you output x1, x2, and xn. So there's a bank of filters. So that you get a stochastic vector on the outside there. And what are we using for these? Well, we're using these one-dimensional. Look at them. Remember complex analysis now? Remember complex analysis? These are the Cauchy kernels, right? And what do Cauchy kernels do when you integrate them? They evaluate, right? Okay? So they evaluate. And so they evaluate. This is what we want to do. So we evaluate at these points. And of course what we get here is this, and here we have something that we can estimate, because this we can estimate, right, by some ergodic estimate, right? From looking at output data. And it turns out that we take a covariance matrix of this. We get this matrix. What is matrix is that? That is the Pick matrix, right? Which is like the tuplets matrix for the other, for the covariance extension problem, right? This is a Pick matrix we get out of this. Okay? So, two sets of tuning parameters, filter bank poles, spectral zeros. Okay, let's do this here. Okay, here we have two lines. They are 0.11 radians around away. And do the parallelogram, you can certainly see these two lines, right? And here you can see them also. This is actually the default setting of this thing that we have, right? And this is actually estimation of spatial lines in color noise. Where the color noise is here, right? Now, I won't play a bad thing here. You see, I just look up my book, textbook of fast Fourier transform. And I know that there is lowest level of resolution. It depends on the number of data and how close these things are. So I choose an example like this, where separation between them is this. And this has been chosen cleverly so that the fast Fourier transform would fail. While this still shows it, you know. These are not so good simulations. These were something that we did when we wrote this paper a long time ago. We should do some new things. But this is basically the idea, right? So by zooming in, you can get the local information, right? Okay, what about robust control? Look at this guy going down here. They're doing it very robustly, right? Look at this. Okay, so, well, we're working on category functions, but as I said, we can also do positive real functions. But we can also do sure functions, right? And we can do a lot of other such, like doing Möbius transforms like this, right? And you can use the same paradigm. So let's say that we do loop shaping in robust control. I mean, let's say that you have a plant, you have a compensator, you have an input, you have a disturbance coming in the output, right? And if we go from the disturbance to the output, we get the sensitivity function, right? The sensitivity function, of course, plays a very good role in robust control. And what is it we want? We want to have internal stability. To have internal stability, what is the sensitivity function to the analytic outside of the unit circle. We like it to interpolate the unstable poles to 0 and the unstable zeros to 1. Okay? This you can look up in a book, for example, Doyle Tannenbaum, Francis and Doyle, this little nice book, short book, will explain this very well. And we want to have disturbance attenuation. We would like the H infinity norm to be small, right? We bound it. We would like to also the degree be small, because we want to have the feel of the system. We have a loop and we have control from outside. We want to feel like we can feel the system, right? And so here it is. You see, there is a minimum bound, which is usually determined. But we're not going to use the minimum bound. We're using a suboptimal bound. And then we take this S, we take it, evaluate the S inverse, and we divide by this. And what are we getting? We're getting a function here that maps the disk to the disk, right? We get a sure function, right? Okay. And of course, we interpolate. So F is going to interpolate also, right? So we have a Nevanlinna-Pick interpolation for sure functions, like this. And the interpolation of degree at most n are parameterized by the spectral zeros in a one-to-one fashion, right? Now, let's give a simple example that we can do by hand. Here is a plant. It has a pole, unstable pole at 2, so that has to go to 0. It has a 0 at infinity, so that has to go to 1. And we want to find all s of degree at most n that satisfies this. And of course, there's only one parameter left, because this is going to be this, and then we have the same thing here. That's going to take care of this thing, right? And then we have one free parameter, namely the pole, which has to be -1 and 1, right? And the optimal phi is 2, so we choose 2.5. And then we get a border diagram, and we see that if we just done the optimal one, which is usually suggested, and then you would have just this one here. But here we get all of these. And perhaps we are doing, we'd like to have low sensitivity for low frequencies, you know. Then we choose maybe this one instead, you know. Now this is a simple example that you can do by hand, but I mean, basically this is the point. But now you know need the convex optimization and all that, precisely what we did before. Okay. Here's an example that I took from Dory Francis and Tannenbaum, or we did. There were two students who were doing this. Here's the. Now I go to the continuous time. It doesn't matter. We just do these Möbius transforms and doing all of these things, you know. And we have compensator, we have step reference, and we do this. And what we want to do with specification, we want to assign a strictly proper K, so the closed loop system is internally stable and satisfies the specifications here. Settling time at most 8 seconds, overshooting goes 10%, and the controller must be bounded, right?
And this just burns in my soul. Is there any rational reason why you need 4 decimal places in this example?
Well, because it comes from Dory Francis and Tannenbaum. You can call any of them and ask. Because we compared with the solution they had. So that's a good, that's a good, I never thought about this. And I've given this talk several times. But I think that the real people to ask would be one of these 3 people. Then they probably forgot why.
There can't be a reason.
Well, there probably is a reason. And maybe they've gone backwards. Yeah, I don't know.
It is just disgraceful.
Yeah. We write the petition here and send to them, right?
Even one that has 7 digits, the bottom 139.
Yeah, look at that.
I mean, yeah.
Look at this, yeah. Yeah, well, yeah, the one there, what is he doing?
You know,
Well, what about those 2 extra zeros?
well, that's irrelevant, really.
Yeah.
But honestly, if a student turned this into, if a student gave me this, I would flame him.
You would?
Yeah.
Yeah. Because you can't have it,
As a student in engineering, I mean, mathematicians can do whatever they can please.
Yeah.
But
I think it's a good thing that these guys already have their PhDs, right? Okay. No, next time I see one of them, I'll bring it up.
tell me the answer.
Yeah. But anyway, what they did was they looked at this and what would be a good thing to do? They would say, this is, look, here now you don't have this anymore. They said, this is the idea of S. You see? And now, what is wrong? Why not use that? Because it doesn't interpolate. It's just a shape they put up, right? It doesn't interpolate. So this is what they want to do. And here is what we do now. We do internal stability requires. Now we take the degree of this to be 4. So first of all, unstable plan poles. You're going to get both of those to 0. I mean, I'm doing this more general here. This going to this very nice number here. Still is rational though. 2, 1. This is non-minimal phase plan zeros, and the other one is a strictly proper controller. So we do all of those things. Now we choose, or actually the students that did, I have their names down here, Lindquist and Agamona. We use this spectral, square of the spectral zeros, right? The spectral thing. And this is Anders Blomqvist, and actually Anders Blomqvist is out and making money in the financial sector. Now the owner is actually a professor at the University of British Columbia in Vancouver. He was first a student I gave his undergrad at Kimura, and then Kimura sent him over to me. Very diligent guy. He and very good, right? So here you see what he does. Here is what you want to achieve. And the red one is what Doyle, Francis, and Tannenbaum are using. Because that's what they get by just not changing doing the maximum entropy, so to say, right? And here, the blue one is what we get, what they got here. This looks very much like the ideal one, right? So it's tuned to be look like the ideal. And what is happening is actually that the red one, the one using just the general theory, will be a degree k equal to h, but you get half of the degree by tuning, right? And the step response looks better. And the control signal is fine also. So you will satisfy those things, right? So you can actually, what we've done is to tune this, of course, by changing the spectral zeros. That's what they did. We recently worked on a multidimensional moment problem, where this is a non-negative measure on some compact subset of RD, and these are linear basis functions defined. So this is you can do for imaging, etc. We have several papers on this that's recently been Simon controllers and etc. Other journals. And here is image compression. We take this usual thing, Lindquist, right?
Yeah, that's not to do that anymore.
You can't do that.
Not,
We stopped about at least 20 years ago, I think.
yeah, that's pretty.
So we are
Pretty much a
actually,
Trump type thing to do.
is it trauma? But they invited her. Yeah, because we're not showing the rest of the big picture. Yeah. You know? So you think I'm not politically correct?
Right.
Okay, sorry. Well, I have to tell my student because I didn't choose the picture.
I was attacked on this.
Oh, you were?
Oh, yeah, I mean,
Right here, by a lady.
Oh, really? Really? Oh, I
I
see.
was called sexist, and I said, look, this is the picture I showed. If you have something else in your head, maybe you are the sick person, not me.
Yeah, because I mean, I think it looks it's a nice picture. Yeah, right? So,
it is. It would be harmless if people didn't know where it came from.
No, it's an interesting picture because if you look at the details, they have a lot of difficult parts of the image that you have to reconstruct.
yeah.
It's the feathers in the hat that really matter, but nonetheless. I mean,
Yeah.
So
Yes.
next time I gave a talk, I came with a baboon.
Yeah. I
I
see.
said that you have a problem with baboon?
Yeah.
Oh, the baboon was a picture, not that you brought one with
It
you.
was a baboon picture, and then I said, now, how do you know it's female or male? So maybe you can attack me on this basis.
Yeah. Well, it's clearly. Yeah, no. Actually, I'm probably a very old-fashioned guy. You know, I'm not only old, I'm also old-fashioned. I haven't learned these things yet. But my young student, former student, Johan Carlson, and Axel Ring, who is our common student, very clever people. They're younger than me, but nobody seemed to have objected to this. Right. Okay. Actually, I think, did we have this in our sign paper? I better check, you know.
It's okay.
Oh, yeah. Model reduction. This is something that I sort of, actually Antulas was working on this type of thing, and they had to build a service. So they, you remember this? So they had this original system and they want to reduce it to this. But if you do it, our thing, we have a third degree, you still get this. And look at all the digits, right? But this is computation now, right? Yeah.
Well, but it raises the question that I was really asking, which is, you know, in interpolation, you really make the requirement that you exactly cancel.
Yeah.
But in the real world, that's never possible.
Yeah, I know.
So, to what extent are these results sensitive to small changes in the number?
Well, you sort of impose, really, don't you?
But what he's asking is, if the map from numbers to model is a stable map, or is it?
Right.
Yeah, that's what I don't understand.
And most of these things are not,
You know, yeah.
unfortunately.
Unfortunately, yeah. Well, I mean, this is This is one of the, you know, there are a lot of things here that that one sometimes, you know, that one can discuss from this point of view. But I'm really giving here sort of a paradigm. For how, and mostly it's my students that have done simulations. That's usually the case. You know, I was brought up before the invention of the electron.
But has anybody in this area done these programs with the additional constraint of the map being stable?
I don't know.
Because, you know, there are particular things from ancient circuit theory and others like, you know,
Yeah.
particular slices and Bldg products and other things that they have inherent stability.
Right, yeah.
It goes all the way back, you know, if I want to go from numbers to a realization, right?
Yeah.
If I do it with minimal realization, it's highly unstable. If I do it so that it's stable, different structures appear.
Yeah, okay.
And this leads to different factorizations of the rational function.
But here you actually, okay, you pose it.
And since you're doing global analysis, it could be done. You could actually ask whether the map
Right.
it has certain sensitivity bounds. Okay?
Yeah. That's a good problem. You might give that to a student. I mean, that's very good. Yeah. No, that's a good research problem.
And maybe in this case, the little numbers will disappear. Never mind.
Right.
Better.
Yeah, I'll talk with you about this, because, I mean, you have some...
But I'm doing things like that now in a completely different way. We'll talk about
Yeah, okay, very good. Maybe it might be also good to do it. Okay. But let's say this. So here is the thing. I mean, here was the original system of Bldg.
Yeah.
And with the two lessons on this thing is the red, I think. No, it's the green. The green, you see. And then the system valid interpolation here. And the blue is a stochastically balanced truncation. And this one is the best. This is why I show it. Yeah. So here's a large scale problem with the CD plane, going from 120 to 12 by reduction. And actually that doesn't work too well with that because something. The real one is here behind. This is the one behind. Yeah, the dotted one that you can almost see, the original system is sort of, yeah.
But what is the range of frequencies that you care about?
Yeah, that's a good thing. That's my question.
Because you sometimes don't care about.
No, precisely. Yeah. But anyway, let's not look at the applications per se. Let's look at the problem of interpolation, of reduction. Then, if you do it like this, you can actually get one that is 12 degrees that looks like this. Now, whether that, for this particular thing, if you're not interested in the full spectrum, like we weren't in the zooming in thing, but let's say that we're just interested in that, now the full spectrum, that gives a better reduction.
Yeah.
You almost never care about the full spectrum.
No, sure. I don't know, yeah, fine,
And that's
fine.
what makes the control work, because you know
Yeah.
that you're going to have increased sensitivity at some range of frequencies.
Yeah.
And
Good point.
you know those frequencies don't matter. And that's really what happens.
Good feedback. All right, so this is what we can do. Okay, here's some conclusion. I could give you some other examples, but I think my time is out. So we have an enhanced theory for generalized moment problem that incorporates rationality constraints described by applications. And we have complete parameterization solutions with smooth tuning strategies. And we have a global analysis for the static class of solution as a whole. And we have convex optimization for the determining solutions. So this is basically the paradigm that I'm trying to explain. And this has been, you can do a lot of other problems. Of course, there will come up other problems, like the one you were discussing and mentioned here, that needs to be taken care of. But I mean, now I'm sort of explaining the paradigm, right, and how it would Thank you.
Thank you very much.